Okay, this is problem 15 on the momentum test review. And this is a video solution for that problem, which reads, at a ballistics lab, a 0.1 kilogram bullet is fired horizontally, so shooting it horizontally into a 5 kilogram block of wood. The bullet embeds itself in the block of wood, and after the bullet is shot into the bullet and block skid across the ground together for a distance of 3 meters before coming to a stop. The coefficient of kinetic friction between the wood block and the ground is 0.4. Calculate the initial speed of the bullet. So another one of these situations where we give you lots of information about after a collision takes place and ask you to figure out what was going on back here before the collision took place. Okay. In my picture, I don't know how well I'll be able to write this, but I should have shown that this distance that it's going to slide ultimately is 3 meters. So we'll try to write a 3 in there. And that seems pretty good. I'm doing that with a mouse pad, so it's not the greatest, but we'll try it. Okay. Again, this is one of those problems where drawing a picture of what's going on really, really helps. This is the before picture. I have a bullet flying towards a block of wood. The bullet's moving at some unknown speed. That's ultimately what we want to try to find. The wood is sitting still. Okay, so before the collision, there's lots of momentum with the bullet. There's none with the wood block. Then the two collide and they start to skid afterwards. And notice how I put point A at the back corner of the block so that you could see that these two are moving. They move past point A. Okay, at this point, the bullet and the wood are both moving at the same speed, which I called V prime. And then after that, they skid for some distance of 3 meters. In my picture, I drew the 3 meters as being a little bit past where my block is right now because I wanted to make it so that friction was still acting on this. After it skidded the full 3 meters, my final speed at the end of that skid of 3 meters is 0 meters per second. Okay, so this is one of those times where you really have to start the problem at the end and work your way backwards to the beginning to figure out what was going on with a bullet. Okay, so what I started off trying to do was figure out, this is where my work started, right there. Okay, so what I started off doing was just trying to use the gang of 5 to figure out what was going on. So again, I was given stuff about final velocity being 0. I knew stuff about the distance it traveled, 3 meters, but I didn't know V original and I didn't know the acceleration. And I knew I needed those things. So to get those, and you can see I guess all that information listed in my variable list there, I said, well, how do I get acceleration? Well, that's why I drew this free body diagram. I knew I had gravity acting downwards, normal force upwards, and I had an unopposed force of friction slowing this thing to a stop. So when I did net force equals ma, I knew this thing wasn't rising or falling, so I didn't have any net vertical force, but I did have a net horizontal force. Well, that force was friction. So I said that the force of friction was equal to m, which in this case is the mass of the block plus the mass of the wood, times acceleration. I also knew that my force of friction was mu times the normal force, and in this problem, normal force and weight are exactly balanced because this object is not accelerating up or down. So those two forces have to be balanced. So I just jumped ahead. I skipped some steps. I said that the force of friction was mu times normal force, where the normal force is the mass of the block plus the mass of the wood times g. And that equals mass of block plus mass of wood, times a. Then I divided by mass of block plus mass of wood to get the acceleration. I plugged in my numbers, and you really can't see it on the screen. So maybe if I scroll down a little bit, you can. There we go. You can see that the acceleration I got was 4 meters per second squared to the left. So this block is moving this way, but its acceleration is directed back that way to the left. Okay. So my next step then was to take this someplace. So I took that acceleration and I plugged it in up here in an attempt to find my original speed of the bullet block combination right after the collision. So this V original is not going all the way back to here. This V original is just how fast is this part of the system, the bullet and block, how fast are they moving right after the collision? So I plugged into some gang of 5 stuff. My acceleration was 4, my distance traveled is 3. 2 times 4 times 3 is 24. I took the square root, I get 4.9. That's my velocity right after the collision. And then it's just applying conservation of momentum from 1 to 2 on this bullet block system in order to be able to get all the way back to figuring out how fast the bullet's going originally. Okay, so there's my bullet block system kind of highlighted in a bad way. It was not my best highlighting. But I know that in this system, if we're looking at just the instant right before to right after that collision, not in the time afterwards where friction has time to act on the system, but just from right before to right after, we can treat it as though momentum is conserved. So that's what I did. So I said the momentum of the bullet beforehand, which is mass of bullet times velocity bullet, plus the momentum of the block beforehand, or the wood beforehand, which is 0, has to equal their combined momentum afterwards. I just found this speed afterwards. That's what this was. Let me go back to pen. That's what this was. So I got that. So I go ahead and solve for the velocity of the bullet. I plug in my numbers, and I find that the velocity of the bullet was 250 meters per second before the collision took place. Okay? So it's really just gang of 5, some forces and friction stuff, using that, and then momentum is just kind of our last step. So that was problem 15.